Hi, welcome to New Electromagnetism V5 early release video. In this video, we're going to release derivations using Vortrix Algebra to not only explain how to use Vortrix Algebra and how to take derivatives of Vortrix vectors, but this is going to set up derivations we're going to need for the final derivation of New Electromagnetism V5, which will be released probably a couple of months from now, if not 6 months from now, somewhere in there. It depends on how quickly things go. Things seem to be going quicker now. So what we're going to derive today is we want to take a Vortrix vector called S and another Vortrix vector called R. Doesn't really matter what these are. One or two Vortrix vectors, and it's a right divide in this form because this is a product of two vectors. It forms a matrix, and so we designate that by putting the matrix bracket around them. And we're going to take the derivative of this with respect to time. Okay, the only thing that we are going to say is that R is basically this is a system of particles. And there's two particles, a source particle or a source particle and a target particle. And the radial distance, not radius, radial distance from the source to the target is defined as R, and R is equal to the position of the target minus the position of the source. And we made, in the previous video, some other derivations using R as well. We can actually put those identities up here now. R dot is equal to velocity of the target minus the velocity of the source. The derivative of the magnitude, or the magnitude of R is equal to the square root of R squared. Again, these are not inverting operators. This is a scalar. Okay, and then we had the direction vector is equal to R over the magnitude of R. And the derivative of the magnitude, not the magnitude of the derivative of the magnitude is equal to our direction vector dot R, which is equal to direction vector times velocity of the target minus the velocity of the source. These are matrices. These must be kept together as scalars. Put my little direction vector thing up there. Okay, and this could also be written the other way around. These can be swapped. These can be swapped. You know, you can put the direction vector on the other side. Doesn't matter, but these must be kept together. Oh, this is a dot product. Okay, again, keep together because they form a scalar. And because they form a scalar, other vector multiplies can pass through them from the right or the left without being affected. That was one of the many landmines that I hit. So the way we're going to pull off this derivation is we're going to use standard derivative notation. And what we're going to do is we're going to say S plus, S is a velocity, and therefore the derivative of S is equal to acceleration. And that would be the velocity of the source. Okay, so source plus the acceleration times delta t, and this is going to be right divided by R plus R dot delta t minus S right divide R divided by delta t. And we're going to take the limit of this as delta t goes to 0. And that's going to be our derivative. Ooh, I got sweaty palms. All right, so because this is right divided in the denominator here, then we have to right multiply to cancel it. And so we're going to right multiply the top and the bottom by this denominator here. And that's going to leave us with S plus acceleration delta t that's now a vector, minus S over R times R plus R dot delta T over delta T times R plus R dot delta T. Now we're going to multiply this through. This is S plus acceleration delta T minus S over R, right divided times right multiply, cancels the R. So this is just S plus S divided by R, minus times R dot delta T divided by this thing here. These S's cancel. And I'm going to put the, and then once the S's cancel, 1 delta T cancels from everybody. And I'm going to write the remainder down here, A minus S over R, R dot over R plus delta T. And what we can do is take the limit as delta T goes to 0, and that gets rid of the delta T. And then what we can do is we can substitute R dot as VT minus V source. And we're going to separate this, so we get A right divide R minus S right divide R and we have to do the right divide R after this because this, remember, is a scalar. Or that's not a scalar, that's whatever, hold on, I'll get there. And so we can do the R dot divided by R. Okay, remember dividing everything by R. This is, this was right divided. So even though we have a flat bracket, when we apply it to these, we still have to right divide it up here. Okay, so that's why we're still using right divide. Now, all of these we can replace a right divide with a left multiply. So if I use direction vector R, A divided by magnitude R, okay, so we're still dividing by the magnitude of R, but because R is right on the divide, it's left on the multiply, and this is the equivalent of this. And we can do this for these guys as well. And you'll see why that makes sense in a second. Divided by R, multiplying this, and we're going to put R direction vector times R dot. And we're just going to put a square here to represent that guy. And now what we can do, we see here that this can only ever be a dot product now. Okay, so we can replace this with R dot, but we have to keep it together. And then so we're left with R direction acceleration over R minus R direction times velocity over R squared, magnitude squared, and this guy can be replaced with this guy, and we have to keep it together. And I'm going to use this version here, VT minus VS, this quantity dotted. Okay, and that, my friends, is the derivation with respect to time using Vortrix algebra of right divide velocity divided by target, radial distance. And if you are my follower, you can see pretty much where that is taking us. And we're going to take this further for Patreon folks only. The full derivations will be released to the general public, but it's going to be long after the Patreon folks see what's going on.